Okay, so I think in the last video, we looked at this one and I went to the other example first. And then let's look at this one. So in this example here, there's a little bit more going on. So the first thing I notice is that there's definitely going to be an oblique asymptote. But what I also notice is that I can factor in, it looks like there might be some cancellations. So I'm actually going to factor by grouping first. I'm going to factor the first two terms and the second two terms. And when I do that, I can pull out an x squared, and I get x plus 2. And then I'm going to take out a negative, and I get another x plus 2. And in the denominator, that's x plus 2 times x minus 2, difference of squares. So that top, when I factored out that x plus 2, that left me with x squared minus 1 over x plus 2 times x minus 2. Those cancel. So that tells me right away that this has a hole, and the x component is -2, because that's the x value that would have made those factors right here, right? Those factors would have been equal to 0 when x was -2. So I wanted to just cross that out. Now, I know what you're thinking, factor further, and you're absolutely right, because that top now factors into x minus 1, x plus 1 over x minus 2. Okay, so that doesn't really get us any more reduction, but it does show us that there are two x-intercepts, right? Because that's when the top is equal to 0. So I know my x-intercepts are when x is 1 and when x is -1. And I know down here I have a vertical asymptote at x equals 2. And I have an oblique asymptote because my degree in the top is 1 bigger than the bottom. Now, it doesn't matter if you do long division on the original function or the reduced function, because it's going to give you the same. And I think I might choose the reduced function because it's less work, right? So let's do long division. So let's actually divide x minus 2 into x squared. I'm going to leave a placeholder plus 0x minus 1. And so then x times x squared, x times what is x squared, which is x. Subtract the minus 2, x squared minus the 2x. Then when you subtract, you get your 0. 0 minus -2 becomes positive 2x, and carry down your 1. One more time, x times what gives you 2x, which is a 2. So 2x, and then 2 times -2 is -4. And then when you subtract -1 minus a -4, it's a 3. Now remember, that's the remainder. And in order to check if it's a cross point, we set the remainder equal to 0 and solve. Well, this never is true, right? 3 is never 0. So that tells me in this function, there's no cross point. Okay, but what are some important things, right? Again, I know that the oblique asymptote, is up here. So the oblique asymptote is y equals x plus 2. So that's important. I have my vertical asymptote at x equals 2. And so I'm going to start sketching those in terms of helping me kind of scaffold this particular graph. So I'm going to go ahead and draw a straight line down. There's my y-axis. Coming across, here's my x. We set a vertical asymptote at x equals 2. So 1, 2. Okay, so there's x equals 2. And my lines aren't the super straightest when I'm dealing with writing on my tablet. And then y equals x plus 2. So again, up 1 over 1, up 1 over 1 right there. So there we go. Okay, now I also know I have two x-intercepts, right? 1 and -1. And so if you remember, like this slope, down 1 over 1, down 1 over 1. So this point right here is actually like -2, 0. And then this is our -1. So I know that it goes through here at at 1 and at -1. And then I probably should see, is there any y-intercepts? So remember, for y-intercepts, we let x be 0. And again, you can let x be 0 anywhere from the starting equation to the reduced equation. It'll be the same. So, I mean, if you do it in the reduced equation, you get -1 over -2, which is 1/2. If you do it in the original equation, you get -2 over -4, which is still 1/2. So 0, 1/2 sits right there. So there's my y-intercept of 0, 1/2. I have my two x-intercepts. And, you know, thinking about like bounding by the behavior of the asymptotes, you know you don't cross. You have these 3 points, so you can sort of envision it's just going to arc in that lower bounded region. So hugging the asymptote kind of arcs up and comes back down. Again, almost like a boomerang. And you might find that characteristically that's going to happen a lot, right? So then, and we might have to adjust this because I forgot we have this hole here, so we have to think about that for a second. But then when we come up here, x equals 2, and like if we're on the low side of this vertical asymptote, we're going to end up on the high side up here because of the multiplicity. And again, we can't cross anywhere. Okay, so we can't cross the oblique asymptote. Now, it does say I have a hole at -2. And when you put in -2 to the reduced function, so you get -2 squared, which is 2, -2 squared, which is 4, minus 1, which is 3, and then -2 minus 2, so it's -4. So it looks like there's a hole. I did my math, right? 4 minus 1 is 3, and then that's -3/4. Oh yeah, that's perfect. So there's a hole at -3/4. So -2, -3/4. So there's going to be a gap right there. 1 point that we're just going to have to skip over. So that's our first example of a hole, which is kind of cool. -2, comma, -3/4. Okay. So again, a lot going on in this particular example. But I liked it, and I'm glad we went through it together because I think it helps to hear the explanation and see it as you work through. Okay, then I wanted to do a non-graphing one. I want to do number 6 here on the homework. It says this function has a hole. Find the coordinates of the hole, and then find k. Well, if you know it has a hole, then you know that you have to have a factor that crosses out. So that's what I'm going to actually start here, right? Like I'm going to start by knowing that I know that the x plus 1 has to cancel somehow on the top. So even though I don't know what k is, I know that there has to be an x plus 1 factor for that to cancel. That's the only way to get a hole. And then you sort of work backwards. Well, if you need -3 as your middle term, why not make it x minus 4? Right? Because then that would be a -4x plus x. That's -3x. And so if this were my starting equation, I'd be able to cancel that factor. And so if it were expanded, that would have been x squared minus 3x minus 4 over x plus 1. So that tells you what k is. K is going to be -4. And then how do you know what the coordinates of the hole were? Well, when these cross out, the reduced function is x minus 4. What got crossed out? What got crossed out was when x was equal to -1. So if you take that -1, sub it in here, -1 minus 4, which is -5, there will be the y component of your hole. So now your hole is equal to -1, -5. Okay, hopefully that makes sense. Okay, and then I want to look at one more together. I want to look at 7 because it says that crosses the oblique asymptote. So I don't want to have to actually graph this whole thing. I want to just be able to find point A, like where does it cross? And we said it crosses when you set the remainder equal to 0. So we can do that, right? So we can do long division and say, okay, x squared minus 2x divides into 3x cubed plus 2x squared minus 3x minus 39. So then I do the math, right? It'd be 3x. So 3x times x squared is 3x cubed. and then there's a negative 6x squared. For my mistake last night, I'm so nervous about doing this arithmetic here. 2 minus negative 6 is 8. So I have 8x squared, drop down the negative 3x, drop down the 39. And then we do one more time, so plus 8. So 8 times x squared is 8x squared, and then minus 16x. And we'll do our subtraction. Negative 3 minus negative 16 is a positive 13. X, drop down the 39. Now I can't go any farther, so this right here is my oblique asymptote, right? Even though it didn't ask for it, it says y equals 3x plus 8. Then it says find the point where it crosses. Remember, we set the remainder equal to 0. This one actually worked out nicely, didn't it? So I'm so happy. I'll change colors. We'll go to orange. So 13x minus 39, set that equal to 0. So 13x equals 39, which means x equals 3. Now you can substitute 3 into the original function where all the x's are, or you could substitute 3 into the oblique asymptote. It doesn't matter. You're going to get the same. So again, my suggestion is the oblique asymptote. So y equals 3 times 3 plus 8, which is 9, plus 8, which is 17. So now my cross point is equal to 3, 17. And you're going to find, it takes so much time to graph these rational functions that sometimes I won't ask you to do the whole process. I might ask you to just do one thing, like just find the oblique asymptote, find if it crosses, something like that, so that you're not, it takes some time to do from start to finish every single example. Okay, so you've gone through several graphs and homework exercises. So hopefully that's making sense. Go back, rewatch if you have questions, and then we'll bring everything together tomorrow in class.